സ്വപ്നങ്ങളാൽ ഹൃദയം നിറയെ സ്നേഹവുമായി ആദരങ്ങളിൽ സ്തുതിഗീതവുമായി ജീവിതം കാഴ്ചവയ്ക്കുന്നേ സർവേശ്വര ജീവിതം കാഴ്ചവയ്ക്കുന്നേ തീർത്ഥാടകരാം ഈ മണ്ണിൻ മക്കൾ വിജ്ഞാനത്തിൻ പൊരുൾ തേടുമ്പോൾ അകതാരിൽ കൊളുത്തോ അക്ഷരദീപം സാദരമിവരെ പ്രദീപ്തരാക്കൂ അകതാരിൽ കൊളുത്തോ അക്ഷരദീപം സാദരമിവരെ പ്രദീപ്തരാക്കൂ മനസ്സിലൊരായിരം സ്വപ്നങ്ങളാൽ ഹൃദയം നിറയെ സ്നേഹവുമായി ആദരങ്ങളിൽ സ്തുതിഗീതവുമായി ജീവിതം കാഴ്ചവയ്ക്കുന്നേ സർവേശ്വര ജീവിതം കാഴ്ചവയ്ക്കുന്നേ.
Thank you, Christina. The Mathematics Department of Sacred Art is delighted to welcome you to this academic program. The 10-day National Enrichment Program in Mathematics enhance the mathematical skills and knowledge of aspiring students. Moreover, this program helps in choosing a mathematical career confidently. Now, I would like to call upon Ms. Lynette Rosalind Anthony, Assistant Professor, Sacred Heart College, for the welcome speech.
Good evening. Respected Principal Dr. Sister Irene, our Head of the Department, Ms. Smita Davis, our Chief Guest of the program, Dr. Aparna Lakshmanan, dear faculty organizers, student coordinators, and all the participants of our 10-day workshop. It's indeed a privilege to give a warm welcome to all of you to NEPM 2021. Our principal is such a supporting administrator who is always with our team for any programs or ideas we think of. Welcoming you heartfully to this program, dear sister.
Thank you, Lynette.
Dr. Aparna Lakshmanan, our chief guest of this day. She is taking our first day session of NEPM 2021. She is such an inspiring researcher any math aspirer can think of as a model. So we are very much happy to have you, ma'am, for joining with us today. Welcoming you, ma'am.
Thank you, Lynette.
Ms. Smita Davis, our head of the department, is a constant supporter and guide of all of us, of our department, in any of the event we conduct. And thank you for being with us and welcoming you to this program.
Thank you, Lynette.
Thank you. I'm welcoming all of the organizers, the faculty organizers, as well as the student coordinators to this program. And indeed, the participants of this program is the must, and it is an important factor of this program. So I'm welcoming each of you to this program conducted by Sacred Heart College for Women, Chalakudi. The Department of Mathematics is organizing this program, and we are very delightful to welcome you all to this program. And we are very much hoping that all of you will have a fruitful 10-day session, and of course your math thinking will be enriched with this program. So welcoming all of you with a short words, with some short words, and have a fruitful 10-day workshop. Thank you. Welcoming you all.
Thank you, Ms. Lynette. With great honor and respect, may I invite the woman behind all the successful saga of this institution, Dr. Sister Irene, Principal, Sacred Heart College, for the presidential address.
Thank you. Respected Chief Guest of the day, Ms. Aparna ma'am, the Mathematics HOD, Smita ma'am, and other faculty members, Dr. Vijita, Dr. Nitin, Ms. Lynette, and Ms. Amala. I'm very happy to see that such a wonderful program, that's a national enrichment program in mathematics. That's a 10 days workshop. So compared to other department, I think the mathematics department is coming forward or coming first to conduct such a long workshop that is for 10 days. So first of all, I take this opportunity to congratulate the HODs, Midamas, and all the faculty members for organizing such a wonderful event. Hearty congratulations. And about this event, I see that usually we hear from students that from the schoolings, we hear that mathematics is a tough subject and so on like that. So some students, even when come for admission, they'll ask sometimes they like to take chemistry as main, but if once they hear that the subsidy or the complementary paper is mathematics, they'll be hesitating to take chemistry. But I used to advise them that without mathematics, there is no science. Because without mathematics, there is no physics, there is no chemistry or any other science. If you really go to the research, means higher level, we can see that in any science, without mathematics, we can't proceed. So some students, I hear that they like the astrophysics because they'll be very fascinated seeing some pictures in the skies, many things like that. But once they come to the reality, they see that if they are interested and they'll take the theoretical physics, we can see that without the mathematical physics, we can't proceed in that level. So what I am telling that mathematics is the backbone of all science, and such type of programs, I believe that really it will create some interest in students that because and they must be proud. The students will be at the last they'll be proud that they are the mathematics students. Because if you are going to engineering, if you are going to engineering colleges, we can see that from the first sem to the eighth sem, that means till the end, they must study mathematics. So without mathematics, no engineering, no technology, anything. So I believe that this mathematics students, they have many opportunities, and it will be revealed or it will be made more clear to the students, and really they'll be get more interested in studying the subject because they find that from each and every sessions and from the brochure itself, I came to know that many resource persons, they are from TFR, Bombay, New Zealand, many personalities I see, and even our HOD Smita is also giving one lecture. From all these lectures, I believe that students will really get motivated, and I really appreciate this attempt made by the mathematics department, even though they are quite busy now, because I see that they are having the PG paper valuation and they have the online classes. Many things are going on. Apart from all this busy schedule, they are organizing such a wonderful program. So really, they also, I find that they also love the subject matter. So they are taking this pain and they together work together and made this program a reality. And I believe that this workshop will really create many mathematicians means in the future. So once again, appreciating and congratulating you, and also all my prayerful wishes for this program. And to the students, I want to tell that you must be persevere, means you must be study in this program, and you must attend all this 10 days workshop, and you must not just one day attend and go. you must make use of all these sessions, because all these sessions are handled by different persons and their perspectives will be very different from one person to the other. So all the students really must make use of all the facilities given by the department, and I believe that all my best wishes for becoming a wonderful mathematician. And once again, thanking you for inviting me for this presidential address, and all my prayerful wishes for the success of this program. Thank you.
Thank you, Sister Irene.
Thank you.
Now, I would like to call upon Dr. Aparna Lakshmanan, Assistant Professor CUSAT, for the inaugural address. She completed a bachelor's in mathematics from St. Joseph College, Irinalakuda, and later master's from Cochin University of Science and Technology with first rank. Later, she successfully completed her doctorate from the Cochin University of Science and Technology in the year 2009. She worked as assistant professor at the Department of Mathematics of St. Xavier's College, Alua, for about 16 years. Now, she is continuing her call at Cochin University of Science and Technology. Her remarkable articles on graph theory and discrete mathematics were published in national and international journals. Once again, it is a great honor for me to welcome this mathematic prodigy for the inaugural address.
Thank you, Rose, for that nice introduction. Respected Principal Sister Irene, Head of the Department Ms. Smita Davis, all other faculty members, and dear students or dear participants of NEPM. I understand that this is the second edition of NEPM, and the registration has crossed 300. It's 300 plus, which itself proves that the first edition was indeed a success. I also understand that the first edition was, the inaugural lecture was delivered by my guru, Professor Ampat Vijay Kumar, and hence I do consider it as a privilege to follow his steps to inaugurate the second edition of NDPM. Without delay, only 15 minutes are scheduled for the inaugural function, and we need to talk mathematics more. So with that, I declare the National Enrichment Program in Mathematics 2021 inaugurated. More later. Thank you.
Thank you, ma'am. Now, let me welcome Ms. Vijida Mugundan to propose the vote of thanks.
Respected Principal, Dr. Sister Irene, Guest of Honor, Dr. Aparna Lakshmanan, Head of Mathematics Department, Ms. Smita Davis, my dear colleagues, students, and participants of NEPM 2021. First of all, I would like to extend my thanks to our beloved principal, Dr. Sister Irene, for extending all sorts of support required for this program. I would also like to thank our guest, Dr. Aparna Lakshmanan, for inaugurating this function. We are honored to have you here, ma'am. Next, I would like to thank our head of the department, Ms. Smita Davis, for motivating us to conduct this program. Also, our coordinator, Ms. Lynette Roslin, our colleagues, Dr. Nitin TJ and Amala Mary George. And I welcome all the participants of NEPM 2021 to this function. So, hearty welcome to one and all, and thank you to all.
Thank you, Ms. Our inaugural function now comes to an end. Next, we will be having a session on Introduction to Topology given by Dr. Aparna Lakshmanan. Let me welcome Ms. Vijida Mugundan to give a brief introduction about her.
So our first session is by Dr. Aparna Lakshmanan S., who is Assistant Professor of Department of Mathematics, CUSAT. She did her BSc from St. Joseph College, Irinalakuda, and MSc from CUSAT with first rank. She obtained her research degree from CUSAT in 2009. Her main research interests include algebra and graph theory. She joined as assistant professor in St. Xavier's College for Women, Alua in 2005 and joined CUSAT in January 2021. She is a recipient of several awards and recognitions. To name a few, NPTEL Enthusiast Award in 2020, IMS Prize Group 1 Discrete Mathematics, instituted by Indian Mathematical Society in 2013, Kerala State Young Scientist Award by Kerala State Council for Science, Technology and Environment in 2012. 2 research scholars have completed their PhD under her guidance and 4 PhD works are ongoing. She is an active researcher too, and she has published her papers in many national and international journals. She has delivered many invited lectures, and today we are honored here to have Dr. Aparna ma'am here. So over to Aparna ma'am.
Once again, thank you, Dr. Vijita, for the invitation and for that nice introduction. I thought it's going to be almost same, but then after a stage, you have added more. Thank you for that. So I'll present my screen. I hope it's visible to all of you.
Yes, ma'am.
Yeah. Before starting, I would like to know whether there is anyone who can't follow Malayalam. If yes?
Yes, there are.
Okay, there are. Okay. I just wanted to know whether it will be possible to switch between 2 languages. Sometimes it is more comfortable. Okay. Then,
please English.
Yeah, sure. Okay. So, as I understand, this is not a conference. This is not a seminar, but this is an enrichment program. So, this will be much more like an interactive session. I'll be asking some questions, not that serious ones, just to make sure that you are with me. Okay, so please do respond, only then the program becomes interesting. Yeah. So the title of today's presentation is Introduction to Topology. Just 1 second. Okay. So when we get introduced to one subject, the first thing that you must know is from where that word originated. So the word topology. Any guess, or does anyone know the origin of the word topology? Participants are free to unmute, right? There is no restriction from the side of the host?
No. They cannot mute themselves.
Yeah. So either you can unmute or you can use chat box, your choice.
Yes, Ankit, go on.
Point? No. Any idea from study of geometry? Akhilesh is almost there, but not exactly. That is what I'm going to explain in my next slide. Any idea from which language? The origin of the word topology?
Greek.
Yeah. Exactly.
From topos.
I think it's Al-Shama. Okay.
Yes,
okay.
ma'am.
What you told is exactly correct. The word originated from, I need to switch again. Okay. The word originated from 2 Greek words, topos, which means surface, and logos, which means discourse or study, simply study. Okay. So the word topology means study of surfaces. Someone was pointing out it is study of geometry. Yeah, such a misconcept is always there. Study of geometric properties of objects. Sometimes topology is termed like that, but it's a bit different. It's not exactly study of geometric properties. When you say study of geometric properties of objects, you know, mathematics is a very precise science. Whenever we use a term, we need a precise definition for that. Here we are using the words geometric properties, objects, many words we are using, right? So what does that actually mean? Can you give me some examples of geometric properties? I think I already showed you.
Piano's axiom.
Sorry? I couldn't hear you.
Euclid axioms, Piano's axioms.
I heard the word Euclidean. Yeah, the word Euclidean is of course related to geometry. Any specific property? Okay, no
Area,
issue.
length.
Yeah, area, length, say perimeter, volume, like that. We have our geometric properties. Usually we term these as geometric properties. And what about properties like say color, smell, melting point, conductivity? Those properties are not geometric, that you know, right? So meter, volume, say curvature, length, we can have many such things. These are geometric properties, whereas the properties like color, smell, melting point, conductivity, heat, cold, those properties are not geometric. But how do you know that the first set of properties are geometric and the second set are not? Just because there is a precise definition for properties which are termed as geometric. Okay. For that, we need another definition, this congruence. Let f be a function which is defined from a to b such that distance between x and y is always equal to the distance between the images f of x and f of y. Such mappings are called isometry or congruence. So between two sets, I am defining a distance preserving mapping or a mapping which is invariant for distance. We call that function d as distance function. So such that is an isometry or a congruence. So geometric properties are those properties which are invariant under congruence. Congruence means isometries or distance preserving maps. If you take a distance preserving map, if the property remains invariant, say for example, you have two squares, you are defining an isometry from first square to second square, the distance is preserved. Then if the length, say if it is a square, if the length of the side remains the same, then you can be sure that the area of these two squares are same. The property area remains invariant. So such properties are called geometric properties. So another kind of properties are called set theoretic properties. Again, for geometric properties, we defined isometry and we said that those properties which are invariant under isometry or invariant under congruence are called geometric properties. Like that, between two sets, I can define a bijection. If there exists a bijection between two sets, such sets are called equivalent. So there exists a bijection from A to B. And you take any property which is invariant under bijection or under this equivalence relation, such properties are called set theoretic properties. Say for example, number of elements. If there exists a bijection from A to B, you can be sure that the number of elements in A is equal to the number of elements in B. If it is an infinite set, instead of saying number of elements, we can say that the order of the set. The order is a set theoretic property. Okay. So we have geometric properties, we have set theoretic properties. Like that, we have group theoretic properties. Again, there the objects. Here the objects were sets. In the earlier case, the objects were again two sets. Now, when we move on to when we move on to group theoretic properties, the underlying objects will be groups. So, what are groups? Groups are again sets together with some operator. So, that will be our underlying objects. And between groups, we can have isomorphisms. And the properties which are preserved by those isomorphisms are termed as group theoretic properties. Okay. So we have geometric properties, set theoretic properties, group theoretic properties, and many more. Like that, we have topological properties. Here, the underlying objects will be topological spaces. In the earlier cases, we had sets. When we came to groups, again, we had sets together with some operators. Topological spaces are again sets together with something more that we will see. And the function. In the case of geometric properties, the function was an isometry. For set theoretic properties, it was a bijection. For group theoretic properties, it was an isomorphism. Coming to topological properties, such that function which we consider are called homeomorphisms. So the underlying objects will be topological spaces, and you define a homeomorphism from one set to another. Under that homeomorphism, if some properties remains invariant, this must be true for all topological spaces and all sorts of homeomorphisms defined between them. If for that some properties remains invariant, we call such properties as topological properties. In fact, it is a bit different from the geometric properties. Most of the times they look similar, but there are cases where geometric properties are not preserved, but topologically they are the same. That we can see through examples. So here again we have two things, right? Topological space and homeomorphism. These two are two new terms. So we need to know what is a homeomorphism and what do we mean by a topological space. So first, let me define a homeomorphism. You take any two subsets A and B of the Euclidean space. A homeomorphism is basically a bijection defined from the set A to the set B, which is continuous. Being a bijection, it has an inverse, and that inverse is also continuous. Or we can say it is open and continuous. If inverse is continuous, we can say that it is an open mapping. Okay. So homeomorphism is basically a bijection which itself and whose inverse are both continuous. And we say that two sets are homeomorphic if we can define a bijection from A to B. Okay. So that is the concept of homeomorphism. Here I have given some examples for homeomorphic spaces. Here you have a line segment, and here you can see another line segment, and you can see that the length increased. The distance, it is a geometric property, like, right? Distance is a geometric property. That has varied. That's different for these two segments. But these two are homeomorphic. We can define a homeomorphism from this line segment to this line segment. So these two are homeomorphic. Like that, this is again homeomorphic. From this line segment, I can define a homeomorphism to this. Okay, which will be in turn continuous. So these three. First, and here you have a region enclosed by a closed curve. All these three are again homeomorphic. You can see that geometrically these three are different. Okay, so again I insist that there is a difference between geometric property and topological property. So these three are homeomorphic. Again, these three figures. Here you have a ring structure, and here you have a teacup, and this, believe me, this is a needle. Okay, a needle structure. For needle also, there is a hole, right? That hole corresponds to this hole in this ring, and this part is extended. Again, these three figures are homeomorphic. Then why people are relating topology to geometry? As evident from this three set of examples, geometry and topology, geometric properties and topological properties are different. But still, people are relating topology to geometry. Why? There is a jovial name for topology, say rubber sheet geometry. Topology is geometry, but not done in a solid plane or a solid face, but in a rubber sheet. So in a rubber sheet, if you draw a straight line, and if you just stretch the rubber sheet, you get a longer line segment, right? And if different people are holding from different sides and stretching with different strength, this straight line segment will become something like this. That shape also get distorted, right? So that is why topology is sometimes termed as rubber sheet geometry. And that is why sometimes topological properties gets confused with the geometric properties. Again, you can see you draw a circle in a rubber sheet. And if you stretch the rubber sheet properly, in a desired manner, you can definitely get a square from that. Even a rectangle or any quadrilateral or any closed polygon or in general, any closed curve. You can make the circle into any shape you want of that of a closed curve. So these two are like that. Okay. So topological properties are related to geometry in the sense that we can call them as rubber sheet geometric properties. And here you have some other examples which are not homeomorphic. You are allowed to stretch a line segment as far as you want, or you are allowed to distort it into any shape, any curve-like structure, but you are not allowed to cut it into two pieces. So the structure cut into two pieces, give me this. Maybe the length of these two, the sum of length of these two will give the length of the first segment, but still they are not topologically or they are not homeomorphic because they are cut into two pieces. Again, cut into three pieces, they are not the same. Now, here you have a circle. If you just twist that circle, you will be getting this H-shaped structure, right? But these two are not homeomorphic. Again, try to make a circle into the shape of an 8 by just stretching the rubber sheet in which that circle is drawn. I'm sure you won't succeed. Okay, so these two are not homeomorphic. Here, there is no intersection. For the boundary, for this boundary of the circle, it is not intersecting with itself, right? But for this figure, there is one such intersection, and that intersection causes problem while defining the homeomorphism. Again, these three structures are not homeomorphic. And again, you give me a circle and make a hole inside that. These two structures are not homeomorphic. If you make two holes, again, it is not homeomorphic to the first one or the second one. If you make n holes, that will be again different. Again, if you take two circles which are close enough, still this structure won't be homeomorphic to the first structure. Yeah. Moving to 3 dimension, you take a sphere. You take a sphere with a hole. These two are not homeomorphic. And one of the favorite examples of all topologists is the Mobius strip. Do you know what is a Mobius strip? Anyway, I'll show you. I'll show you what a Mobius strip is. Okay, you take a paper. You take a long strip of paper and stick the two ends together. What you get is a structure like this. Okay, this is not Mobius strip. You are getting a structure like this. You are getting a almost a ring-like shape. Again, you take that same paper strip. You just twist that. You just twist the paper strip and then glue. What you get is a shape like this. So, are these two homeomorphic? That is my first question. You are just gluing two ends, you're getting a structure like this. And if you glue after just twisting, you get another structure like this. Will these two structures be homeomorphic? As time demands me to be a bit fast, I'm not waiting for the responses. These two are not homeomorphic. In fact, we can prove that these two are homeomorphic in a simple way. For this structure, we have two faces. You have a red face, which I call as inner face, and a blue face, which I call as outer face. If someone wants to move from the inner face to the outer face, they need to travel through the edge. Either through this upper circle or this lower circle. There are two edges, an upper edge and a lower edge. They have to transverse either through the upper edge or lower edge. So here, in this case, you have two faces and two edges. But when you just twist it and then glue, say if an ant starts from one point in the red face and simply move through the surface without cutting the edges, that ant can reach the red face also. Start from red, you can move to blue and then come back to red is possible. Okay, so there will be only one face and one edge. This structure is called a Mobius strip, and that is totally different from the one which we get by simply gluing the ends of the paper strip. So this is a Mobius strip. So that is the idea of homeomorphism. Next, we need to move to topological spaces. Before moving to topological spaces, let me define something else, a metric space. A metric space is a set together with a function, that function which we call as a metric, which satisfies certain properties. So a metric is a function defined from x cross x to R, say, which satisfies three conditions. The value of that function must be non-negative. It must be greater than or equal to 0. And d of xy will be equal to 0 if and only if x equal to y. And this function must have a symmetry property. D of xy must be equal to d of yx, and it satisfies the triangle inequality. D of xy plus d of yz will be greater than or equal to d of xz. You move directly from x to z. That will be shorter compared to you move from x to an external point y and then come back to z. Okay, that makes sense. Such functions are called metric, and a set together with a metric is called a metric space. Once you are given a metric space, I can define open sets. To define open sets, I need open balls. So first we will define open balls. The technical definition goes like this. Let x naught element of x and R be a positive real number. Then the open ball centered x naught and radius R is defined to be the set, the collection of all x element of x such that distance between x and x naught is less than R. Simply, an open ball is the collection of all points which are at a distance less than R from a fixed point x naught. This distance R is called the radius of the open ball, and the point x naught is called the center of the open ball. When we define open ball, it is quite natural that if you are thinking in a two-dimensional level, a circle will come to your mind. And if you are thinking in a three-dimensional level, a sphere will come to your mind. But that is not necessary. That depends upon the space which you choose. It need not be a circle. It need not be a sphere. It need not look like anything similar to a circle or a sphere. The only thing is that the notion distance less than R make us think that it is a circle or it is a sphere like that. That's not necessary. Say, for a simple example, if my space is real line, if I am taking the real line and apply this condition, what you get is an open interval which is centered at x naught. Say x naught minus R, x naught plus R. That open interval will be our open ball. It is not like a circle or a sphere, right? Again, if we are considering different spaces, the shape of that open ball can be totally distorted. Okay, so that's it. It's not necessary that that ball is connected also. We haven't introduced the concept of connectedness. Still, I say that an open ball need not be connected. If the space is not connected, obviously, that happens. Okay, so that is the concept of an open ball. We say that a set A subset of X is open if any point in A can be inscribed in an open ball such that that open ball is contained in A. Okay. So you take any point x naught, you are able to find a radius number R obviously greater than 0 such that the ball centered at x naught and having radius R is completely contained inside the set A. Please note that the value of R totally depends upon x naught. If we vary x naught, if you take different x naughts, the radius R can also vary. It's not necessary. Say something like that in the case of uniform continuity is not here. Okay, it can depend upon the point which we choose. When we change the point, the radius vector also change. That is fine. The only thing is that we need to find one non-negative switch number R. So these are open sets. From the definition itself, it is easy to follow that every open ball is an open set. If you are given an open ball, you take any point, we can easily find an open ball which is contained inside there. Just some Euclidean adjustments are required to choose the radius vector r. We can choose it as the minimum distance towards the center and r minus that distance. You choose any radius less than that, you get an open ball which sits inside the given open ball. So every open ball is an open set, but not vice versa. Every open set need not be an open ball. In fact, open sets will be union of open balls. The first theorem about metric space. Empty set and full space are always open. In empty set, there is no point to contradict the condition for an open set, so it is open. For full space, you take any point from the full space and any open set containing that point. Obviously, that will be contained in the full space. Open set I am taking from the full space, right? So full space will be always open. So empty set and full space will always be open. You give me an arbitrary collection of open sets and take the union. That union will again be an open set. Why? Say I am taking GI as a collection of open sets and I define G as the union of GIs. You take any point X from G, that X belongs to at least one GI, right? G is the union of all GIs. So X belongs to some particular GI naught. GI naught is an open set. So I can find an open ball centered at X and contained in GI naught. G is the union of all GIs. So this open ball will be contained in G also. So you give me any point from G, I can always find an open ball which is contained in G. So arbitrary union of open sets is open. Again, finite intersection of open sets is open. You give me open sets G1, G2, etc. Gn. I define G as the intersection I equal to 1 to n Gi. You give me any point from G. It is intersection of GIs. So X belongs to GI for every I. And each GI is open. So corresponding to each GI, I can find the radius number Ri such that the ball centered at X and having radius Ri is contained in GI. Now, you take a ball which is centered at X and having radius small r, and another one again centered at X and having radius capital R, and small r is less than capital R, then obviously that smaller ball will be contained inside the bigger ball. That is the idea that we are using here. We are taking R1, R2, etc., Rn, the radius vectors. There are only finitely many, so I can take minimum. So choose the minimum as the radius R. Then that ball will be contained in all other balls. Each ball is contained in GI. So our smaller ball is contained in every GI and hence in the intersection. So I have obtained an open ball centered at X and contained in G. So G is open. Okay. Why we need that finite condition? If we take arbitrary intersection, then we have a collection R1, R2, etc., Rn. Okay, instead of choosing minimum, you can go for infimum, but that infimum may be 0. Even if you take a collection of non-zero numbers, the infimum could be 0. Say, for example, if you take the collection 1, 1 by 2, 1 by 3, 1 by 4, etc., 1 by n, etc., 0 is not a point in that set. But if you go for the infimum, what you get is 0. Our radius vector cannot be 0. So such kind of proof cannot be extended to arbitrary intersection of sets. In fact, arbitrary intersection need not be. I can't say is not. Sometimes it is, but need not be. It's not always open. And this theorem gives one more property of metric space for which I'm not interested for the time being. Okay. So we have three properties. Empty set and full space belongs to tau, where tau is the collection of open sets. Tau is closed under arbitrary union and tau is closed under finite intersection. This is the base for defining topological space. For defining topological space, again like metric, for metric space, we had it set together with a metric, right? So when we move on to topological space, we will have a set together with something which we call as a topology. That something is denoted by the letter tau. Tau is basically a subset of the power set of X. Again, tau satisfies the three properties which we found true for the collection of open sets in the case of metric space. That is, empty set and a full space must be elements of tau. Tau must be closed for arbitrary union and finite intersection. If these three properties are satisfied, tau is called a topology, and a set together with a topology is called a topological space. Again, when comparing with metric space, obviously we have the tendency to call the elements of tau as open sets, which we do. Okay, so elements of tau are called open sets. From the direction which we came, it is clear that open sets in a metric gives us a topology. So if a topology is obtained from a metric, we call such topologies as metrizable. Okay. So give me a metric, I can generate a topology from that. Such topologies are called metrizable topologies. But in general, it is not true that every topology is generated from a metric. We have plenty of examples to prove that there do not exist a metric which generates such and such topology. We'll have some quick look to the examples of topological spaces. The first condition for topology is that empty set and full space must be present. So you take any topology, empty set and full space will be there. What more? If I don't add anything more, that is just simply empty set and full space, then it is closed under arbitrary union and finite intersection. So it forms a topology. That is too trivial, right? Such topology are called indiscrete topology. That is a topology in which the only open sets are empty set and full space. What will be the opposite for that? You take any subset of X. All those sets are open sets. That is, so I am taking as power set of X. Every subset of X is an open set. If I define like that, again, definitely it will be closed under arbitrary union and finite intersection. For subsets are closed under arbitrary union and finite intersection. That topology, the other extreme, that topology is called discrete topology. Another one is cofinite topology. Open sets are those whose complements are finite. Okay. It's not necessary that set itself is finite. Set can be infinite. Say if a set is finite and its complement is also finite, means the space which we are considering is finite. If the space which we are considering is finite, then for every set, the property that the complement is finite is satisfied. So in that case, cofinite topology reduces to discrete topology. Both are same. Cofinite topology is same as discrete topology if the space under consideration, the set X, is finite. That's not a good case, right? That is not a good example, right? So we consider infinite spaces, but then there is another problem. We need empty set to be present in every topology. The complement of empty set is the full space. But we say that the full space is not finite. So the condition complement is finite is not satisfied. So when we define cofinite topology, we say that empty set together with sets with the property that the complement is finite. Empty set need not have that property. If empty set also has that property, then what happens? Cofinite topology becomes discrete topology. If you want them to be distinct, the space X must be infinite. If X is infinite, for making cofinite topology a topology, we must insist that empty set also is to be added. Similarly, we can define a co-countable topology. That is, open sets are those whose complements are countable. Again, if the space X is not countable, we must insist that the empty set is also included. Empty set together with sets whose complements are countable. That gives another topology called co-countable topology. We say that a topology tau1 is weaker than tau2 if tau1 is a subset of tau2. That the collection of open sets becomes bigger, the topology becomes stronger. Okay, so weaker, stronger. Similarly, we call them coarser and finer, or smaller, larger. All such terminologies are used by different authors in different textbooks. Weaker, stronger, and smaller, larger is fine, but the term finer is sometimes confusing. When you say that tau1 is finer than tau2, we we get a feeling that tau1 is small. Finer means we get an illusion that it is small, but that is not the case. Tau1 is finer than tau2, then tau1 is a superset. So only that name is a bit confusing. And as we have already seen, any topology must contain empty set and full space. So every topology will be stronger than the indiscrete topology, which contains only the empty set and full space. And discrete topology contains all the subset of the power set of X. All elements in the power set of X are present in discrete topology. So any topology will be weaker than the discrete topology. So such a hierarchy is there. In discrete topology will be weaker than any other topology, and every topology will be weaker than discrete topology, or in other words, discrete topology is the strongest of all topologies. More examples. Usual topology. Usual topology is generated using Euclidean metric. You take the Euclidean metric, every metric generates a topology. The topology generated using the Euclidean metric is called usual topology. Then semi-open interval topology. In that, the open sets are semi-open. That is, one side is open and other side is closed. One thing you have to be sure, either you have to take sets of the form, initially it's open, say open A, closed B type sets. That gives me a topology. Or closed A, open B type sets. That also gives me a topology, but you can't mix both. Both are semi-open, right? Open A, closed B, and closed A, open B. Both are semi-open, but you can't mix these two. If you mix these two, what happens? Say you take, closed 0, open 2. Then say open 1, closed 3, and take the intersection. What you get is open interval 1, 2, which is not semi-open. Okay. So even the name suggests semi-open interval topology. You have to make sure that either you take sets of the form open A, closed B as open sets, or sets of the form closed A, open B as open sets. So that is semi-open interval topology. Then scattering topology. That is not a famous one, but an interesting one because it serves as a counterexample for many results which we may think as true, but in fact is not. Scattering topology means the open sets are of the form A union B, where A is an open set of R with usual topology and B is any subset of irrational numbers. So usual topology will be weaker than scattering topology because empty set is a subset of irrational numbers. So A union B is A itself, right? So every open set in an usual topology comes in scattering topology also, and scattering topology is stronger. It has many more elements, many more open sets. Then open rays, the open rays, A infinity type rays. If we define those as open sets, that again gives us a topology. Then order topology, then Sierpinski space topology. I'm not explaining because I'm almost exceeding. There is all chance that I exceed 6 p.m. I don't want that to happen. Okay, this Sierpinski space topology is again interesting. Say empty sets. The underlying set contains only two elements, A and B, and the topology contains empty set and full space and one singleton set. Okay. So that is Sierpinski space. Sierpinski space also helps us in many ways. So given a set, I have defined many different kinds of topologies. For R itself, I have shown 4 topologies in a single slide, right? So given a finite set, how many topologies are there on that set? You are given a finite set with n elements. I'll spend 1 minute here. You are given a finite set with n elements. How many topologies will be there? Anyone there? Any answers? Band? I don't understand. How many topologies are there on a finite set with n elements? That's my question. Okay, I leave it as an open question. You can think over it later. I don't ensure that there is a definite answer. You can think over it later. Okay, at least for some bound you think. Maximum how many topologies can be there? Okay, so that's an open question for you. Now moving to another concept, convergence. Let Xn be a sequence in a topological space. The usual concept of convergence holds here also. The sequence Xn is said to converge to a point X. If you give me any open set U which contains the point X, there must be a stage capital N, beyond which the sequence entirely lies inside the set U. Okay, the technical definition is given here. For a better understanding, I just said like that. Beyond a stage, the sequence is here, sequence is approaching X. After some stage, you can be sure that every point of the sequence is inside that open set U, which contains X. If you change the set U, the value of N may also change, but for every open set, there should be some such N. That is, the sequence come closer to X after certain point, and it never goes away from X again. Okay, that is what we need for convergence. Okay, so we have indiscrete space, right? We'll just think about the convergence of a sequence in an indiscrete space. What happens? Again, as there is lack of time, I'm not opening the forum for you. I'll just tell you the answer. In indiscrete space, an interesting thing happens. Every sequence converges to every point. Say, in Malayalam, we say Samatva Sundaram. All are equal. All are equal. You give me any sequence and you give me any point, that sequence converges to that point. That is what happens in an indiscrete space. But why? You give me any sequence Xn and any point X. To think of convergence, we need to take an open set which contains the point X. In indiscrete space, the only open sets are the empty set and the full space, right? So if we need to take an open set which contains the point X, then the only possibility is to choose the entire space X. And the entire sequence lies in that space X. So we need not go on looking for N. You can take N equal to 1. The entire sequence is in that open set itself. Okay. So in an indiscrete space, an interesting thing happens. Every sequence converges to every point. Okay, then what happens in a discrete space? In a discrete space, you give me any point. Here, every subset of X is an open set, right? So in particular, you give me the point X, you take singleton X, X alone. That also is an open set which contains the point X. And in that open set, the only point is X. So the sequence can converge to X only if the terms of the sequence are all X after a certain stage. Okay, that means only eventually constant sequences converges in a discrete space. Constant sequences, you know, just one term, say 1, 1, 1, 1, etc. or a, etc. That is a constant sequence. What is eventually constant? Eventually constant means you are not bothered about first finitely many terms. You write whatever you want as first finitely many terms. But after that, every term is X itself or every term is A itself. Then we call such sequences as eventually constant sequences. That is what we require for convergence in a discrete space. The first finitely many, say that can be 1 lakh, that can be 2 lakh, no issues. Up to some finite stage, you can write whatever terms you want, but after that, every term is fixed, is the same. Then that sequence converges to that constant value. Again, convergence in confined topological space is also interesting. As there is no time, I am not going towards the explanations. In a confined space, convergence happens if and only if at most one term of it repeats infinitely many times. So if 2 term repeats, so I will just tell that part. If 2 term repeats, if the term A and term B, both these terms are repeated infinitely many times, then you consider the set X minus AB. The complement of X minus AB is set AB, which is finite. Okay. So X minus AB is an open set in a cofinite space. You take that open set. Since A and B are repeated infinitely many times, you choose whatever as the value of N. Even after that, the sequence contains both A and B, which is outside X minus AB. So you can't find a stage after which the entire sequence lies inside X minus AB, and X minus AB is an open set. Okay, so it cannot converge to any point other than A and B, and it cannot converge to A since X minus B is an open set which contains A and which do not contain B, and so the sequence cannot be entirely inside X minus B. Similarly for X minus A also. Okay, so cofinite space convergence happens if and only if at most one term is repeated. If one term is repeated infinitely many times, the sequence converges to that point, and if no terms are repeated, then something similar to that of indiscrete space happens. Every sequence converges to every point. So I am now going to the details of the proof. I'll just conclude the session by explaining three types of connectedness. Say simple connectedness, path connectedness, and locally connectedness. Three types of connectedness in topology. Okay, in general, when you hear the word connectedness, what comes to your mind? The general idea is that from any point in the set, you are free to move towards any other point in the set. That is, they are connected. That is the concept which comes, right? You take a space, you take a point A, you take a point B. You must be free to move from A to B within that space. That is the idea which comes to our mind. But in topology, connectedness doesn't mean that. Okay, it doesn't mean that from A to B, I can move like this without moving out of the set. Such a thing is not there. Okay, here, connectedness is something else. Say, in topology, this set is connected. If I just plainly ask whether these two are connected, you see two different objects, right? Two pieces. So obviously you think that it is disconnected. But that need not be true. Okay. Here, let the underlying set be set x1, x2, and let the topology be empty set singleton x and x. That is the Sierpinski space. Okay, I'm considering the Sierpinski space. The Sierpinski space is connected. For I cannot find two open sets, two disjoint open sets whose union is x. That is the concept of connectedness here. Say the space is not connected if the space can be separated into two disjoint open sets. I can write x equal to A union B, where A and B are disjoint and open. If only if such a thing happens, we say that a space is disconnected in topology. Okay, so even if you imagine a figure like this, that need not be disconnected. Okay. The other concept relates to the path connectedness. Okay, there we need a path between 2 points, right? So that general concept of connectedness leads to the definition of path connectedness in topology. So here is the technical definition. A space X is said to be connected if it is impossible to find two non-empty subsets A and B, such that X is equal to A union B, and A closure intersection B closure is empty. It's not necessary that you take A closure intersection B closure, A intersection B is empty, and A union B equal to X, where A and B are closed. That also is an equivalent condition of connected space. You have plenty of equivalent statements for a space being connected. Depending upon the situation, we use whichever definition or whichever equivalent statement which we want. Okay. And the component of a connected space means maximal connected subset. It's not connected means it has a disconnection, right? In that disconnection, you take the maximal connected part. Each maximal connected part gives you a component, and a space is said to be totally disconnected if the only connected components are singleton sets. So if you are taking the discrete space, every singleton set is an open set, right? So if you take two elements, even then that can be splitted as set A union set B. So there is a kind of disconnection. So such spaces are called totally disconnected spaces. So discrete space, we feel that every set is open, so there is something more in it, but in fact, it is totally disconnected. Again, the set of rational numbers, irrational numbers are all examples of totally disconnected spaces. Now, to define path connectedness, we need to know what is a path. A path is basically a function defined from closed interval 0, 1 to the space x, which starts at the point alpha of 0 and ends at the point alpha of 1. It's a continuous function. Alpha of 0 is called, that is the image of 0 is called the origin, and the image of 1 is called terminal. And a space is path connected. If you give me any 2 points x and y, I need to define a path whose origin is x and terminal is y. If such a function exists, we say that the space is path connected. Once path connectedness is defined, the obvious question is, what is the relation between connectedness and path connectedness? From the Sierpinski space, it's clear that connectedness need not imply path connectedness. Sierpinski space is connected but is not path connected. What about the converse? Is every path connected space connected? The answer is yes. And the proof is very simple. Okay. We need to prove that given a path connected space, it is connected. So take a path connected space. You take a path connected space, you take any point x0, you fix some point x0, and let x be an arbitrary point of x. Since the space is path connected, I can always find a path which starts from x0 and ends at the point x. Closed interval 0, 1 is connected, and the function alpha, the path is a continuous function. So the image is also connected. So the point x0 and x belongs to the same connected component of x. And this is true for every x. So every x belongs to the same connected component of x, and hence x is connected. That is how we prove that every path connected space is connected. The third type of connectedness is locally connected. When we learn continuity, we'll say that locally continuous, right? A function which is not continuous may be locally continuous. At some point, it can be locally continuous. And again, local maxima, the concept of local maxima, local minima is there. In the neighborhood, this is the maximum value. So we call it as a local maxima. And that need not be the maxima of the entire set. So such concepts are there, being local. Very much like that, there is the concept of local connectedness. A space x is said to be locally connected at a point x if every neighborhood of n of x, there exists a connected neighborhood m of x such that m subset of n. As I told earlier, an open ball need not be connected. Okay, so you take a point x and take an open ball. That open ball can be disconnected. Okay, let it be. But are you able to find a connected subset of that open ball which contains the point x? Then it is locally connected at the point x. That is the concept of local connectedness. So the next question will be, what is the relation between connected space and locally connected space? As we have already reached 6, again I am not opening the question to the audience. The answer is connectedness need not imply locally connectedness. Okay, something which we do not expect. If it is connected, then it must be locally connected, right? That is what we think, but it is not true. There are plenty of examples to prove that there are connected spaces which are not locally connected. One among them is the comb space. Comb space means it's the union of two sets A and B, where A is x varies from 0 to 1 and y is fixed as 0. That is this part, this interval part on x-axis, 0, 0 to 1, 0. This part is termed as the set A. And set B contains all these line segments of length 1. These line segments are those in which the value of x varies from 0 to 1 and the value of y is either 0 or 1 by n for some n. Okay, so value of n equal to 1 gives me this line segment, n equal to 2 gives me this line segment, 3 gives this one, 4 gives this one, so on, so forth. Okay. This space is connected. That I can prove using path connectedness. You can see that this, all these line segments intersects with this bottom one, right? So from any of these line segment, I can move to any other line segment, just come down up to the line segment from 0, 0 to 1, 0, then move on to whichever point you want and then move up. Okay. So like that, I can move. I can find path from any point in this space to any other point. So this is path connected. And we have proved that path connectedness implies connectedness. So this space is connected. But this is not locally connected. This is not locally connected, which I can prove using the point 0, 1 by 2. You take this point 0, 1 by 2 and take the open ball having radius say 1 by 4. So this part. Okay. This entire half disk is not present. Only those points which intersect with the COM space will be present in that open set. Okay. This is disconnected, right? We have several line segments. So this is disconnected. No problem. Neighborhood can be disconnected. What we want is to find a subset which is connected and which contains the point X, right? And that again gets contradicted because the line segment from this part, the line segment part from the y-axis, that part we expect to be connected, but it is not an open set. In fact, it is not an open set because you take any point and take the neighborhood as n tends to infinity, 1 by n tends to 0, right? So it will intersect with however small radius you choose, it will intersect with some 1 by n1, some line segment of the form 1 by n1. And that gives us a contradiction that it is locally connected. Okay, so we have three types of connectedness: normal connected space, path connected space, and locally connected space. Path connected implies connectedness, but connectedness need not imply path connectedness. And connectedness do not imply locally connected. Locally connectedness do not imply connectedness. Okay, that is the relation between these three types of connectedness. So these are very, say, some very fundamental concepts of topology. Topology is a very vast area. I have just told you some basics of topology. So with that, I conclude. Thank you.
Thank you, ma'am. That was an outstanding and enlightening session on basics of topology. Although we are having a shortage of time. So now it's time to clear your doubts and you can give your feedback too.
Students can post your queries in live chat also.
If there are any queries in the live chat, I mean in the YouTube live streaming chat box, I won't be able to see that. So someone please help me.
Lynette will be taking care of that. I think nobody has posted yet.
Ma'am, please suggest any book for topology and metric space.
I'll go for K.D. Joshi. Am I clear? Introduction Introduction to General Topology by K.D. Joshi. That's good for a startup reading in topology. So I think there are no further questions. Shall we conclude?
So let me welcome Smiji to give feedback about the class.
Good evening all. I would like to thank Dr. Aparna ma'am for taking the time to explain such an interesting topic in such simple words. Topology is a beautiful subject and Aparna ma'am has explained many important definitions and theorems. As I'm a PG students, we have the subject topology. So I think it's really helpful for us. Thank you, ma'am. Thank you for taking the class today. And thank you all students who have joined for the workshop today. Once again, thank you all.
Thank you, Smiji.
Thank you, Aparna ma'am. Participants, please fill the feedback form.
Thank you, ma'am.
Thank you, Aparna ma'am. In spite of your busy schedule, you have found time for us. And it is very kind of you and sweet of you. Thank you.
My pleasure. Am I free to leave now? Shall I leave the meeting room?
Yes,
Yeah,
ma'am.
you are free to. Thank you.
Thank you.
Video